EC 111 Lecture 11 Set 5, the algorithmic flow of the SHA-256 hash algorithm. Now, remember what I told you earlier about, these hash designs are just a recipe of shuffling and making things so that it's hard to go back. Basically, it's just like, shuffling a deck of cards or, having designed something that has these properties satisfied that we just discussed. The properties being, deterministic, unique, pre-image resistance, second pre-image resistant, collision, and avalanche property, which are the main properties what we are looking for. Now, in this particular example that we have, the input message should be limited in the design that we have, and this is not really a problem, but this is just like a design decision. And this is the number we have set is 2 to the power 64 bits, which is not that small, so this should not be a problem for even big files being hashed in this using this algorithm. The message that we are sending to this hash function is process 512-bit blocks sequentially, and the message digest is 256. So imagine that you have a big file, and this file is a lot larger than 512-bit block. But what happens is that this algorithm is going to chop this into smaller blocks of 512. And this smaller blocks, we will be talking about the properties of these smaller blocks. But then, once you have these smaller blocks, then we're going to sequentially send these blocks to the SHA-256. And the reason this is called SHA-256 is because this output is a fixed output value of with 256 bits. So now let's go and take a look at this algorithm which is a simplified one from the SHA-256, which is a standard algorithm. But the reason we're doing that is just to get you familiarized with the steps. And when you're doing a programming for this, it's really kind of like following any recipe. Like, you have to understand what each step is doing mathematically and process-wise on the data, and then just have a controller that goes through this control function and implements them. Very similar to what we've done with, with the steps of this in this class. So remember, we have the SHA-256 algorithm where the input was 512 blocks, and we have to pad a message which could be much larger that 512. We add a single one to the end of M, so we have M, and then we add a single one. But before then, we're going to pad it with zeros until the length of the message is getting to 448 modulo 512. So which means we pad until we get something which has 64 bits less than some multiple of 512. And then once this happens, we use the rest of the 64 bit, which is unsigned. Basically, this is becomes a 512 bit. So in short, what will happen is that we have the message M. We have the message M. In this particular case, this message M is 900 bits. Then we have the number 1 appended to this. Then we have, when we insert, then we have the 64 bits that are reserved here. And this 64-bit is going to contain the size of the file. Remember, the size of the file was limited to 2 to the power 64. This is the reason, because the address bit, the address part, which is 64-bit, is supposed to hold the size of the file. So we have, and then we will have some slots remaining between this 1 and between the 64 bits that we left for the size. So the rest of them in this particular example will be 59 bits. and we insert zeros in these 59 bits. Now we get to a multiple of 512 using this procedure. So if we had 900, we get with this procedure to 1024 bit, which means that we have two 512-bit messages. And remember, every time we're running the SHA algorithm, we're going to insert one of the 512 messages to that. And in the next step is the buffer initialization, and then this is initializing the digest, which is basically the output of the hash function, to preset values. In the algorithm that we have, we are going to set these to preset values that are each 32 bits. And we have 8 of them. And 8 times 32, as you know, is 256. So at the end, we initialize the output to these values, and we are going to process on these values, just like the same way, you basically kind of say that you put all the cards in your hand in a certain order, and then you start to shuffle them. And assume that this shuffling is a deterministic algorithm, but anyhow, that initial value has some impact over what can be shuffled after that. And these are just some values suggested for initializing the hash function, that 256 bits. So 32-bit words times 8 is 256, which we basically initialize the message digest. And the message digest is really that output of the hash function. And sorry for my handwriting. It shows like this, but this surface really makes it hard to write. Now, what happens is that, remember we get this message, which is multiples of 512. What we're going to do is we're going to sequentially process it, which means that we're going to chop this message into 512-bit blocks. In the example we had with 900 bits, this means that we have 2 of these 512 block, and then we're going to process each of these sequentially, one after the other. So in short, the input is the 32-bit word from the message, and then we have a constant array, and then we have the current message digest, which is happening, and then the output is going to be a new message digest. So we initialize this message digest, which let's call the 32 bits that we had 8 of them from A to H, A, B, C, D, E, F, G, H. And let's assign those values that we had as the initialization, H0 to H7, to these registers. Then this algorithm is going to take 64 rounds for processing this 512-bit block. Again, going back to the shuffling example, I'm going to have an initial order for the cards, and I'm going to have a deterministic algorithm that shuffles these. And this is going to be not 1 or 2 rounds, this is going to be 64 processing rounds of this. And then each step, as I said, this is an experimental algorithm. This is an algorithm that was just kind of found to shuffle things well. And the recipe is this: if you're around less than 16, what we are going to do is we are going to assign the next 32-bit word of the block. And if you're more than 16, what happens is that we are going to have an algorithm which takes some of these chops of the message, which are 32-bit chops, and it's going to rotate among these chops and XOR them, and then basically either right rotate or XOR. So these are the two main algorithms that are done, and then it's going to have add some of these values. Again, this may look arbitrary, but this is just a very experimental algorithm that has been designed with the efficiency in mind. So this is basically what happened. And you may ask yourself, why is it only doing XOR and rotation? Why is not using something kind of more sophisticated like multiplication or something like that? You have to keep reminding yourself that multiplication is actually expensive, and we want to make these algorithms to not have a lot of computation overhead. Now, the constant KTs that are given in this algorithm are just listed here. I don't think they would have a lot of meaning here, but they actually do get add up here. So if I see where these KTs come in, you could see that they come in here when we are finding the intermediate values for the step. So basically, this is the details of the step for the steps that go after that original step in step 4. So again, we have some write, rotate, and some XOR here, some addition, and then the T1, which is added to the T2 and goes to the first register, is calculated here. We will go through all these calculations later on in the class, talk about the computational overhead, how you could optimize your design and so forth. But at this level, as I just mentioned, it's kind of a much more of a recipe to you than anything else. We're just basically giving you an algorithm, a recipe, and are asking you take a look at this recipe and see how you could implement it. And then, these basically the content of the register A from the previous one goes here to B, and so on and so forth after we're done with the step. After you process all these steps, what happens is that we are going to use the content of these registers and update the original 8 registers that we had as the initial values with that content of the hash value that we just calculated, A, B, C, D, E, F, G, up to H, and then basically have this H values from H0 to H7 updated. Now, after we process all the components of the message, which were, each 512. So this algorithm that we just discussed works on the 512-bit input. Now you have multiple of them. In particular, for the example we had 2 of them for 1024 bits. Now we do the same, and again, because every time we are just mapping this to that H0 to H7, the message digest or the output is going to stay the same length. And you could find more information about the SHA-2 algorithm we just designed, and this is actually a simplified version online. I'm sure you all know how to use those resources to get your hands on and have more clear understanding. In the next set of slides, we'll be talking about the module interface and the design hints so you could actually better design this SHA-256 function.